Hello everyone. Today we will start with how to design digital filters. There are two types of digital filters. One is recursive and the other one is the non-recursive. In the recursive case, there is at least one feedback path in the filter. But for a non-recursive digital filter, there will not be any feedback path. A linear time invariant discrete system described by the following equation is commonly called a digital filter. So this is the equation actually. Yn is the output. The sigma k going from 0 to capital M with the coefficients represented by a, k, xn minus k. So these are the delayed versions of the input, previous input, minus sigma k going from 1 to capital L, bk. So these are the delayed versions of the previous output samples. These are input samples and these are output samples. This is a general equation. This is a general equation of the digital filter. Now this portion of the equation actually represents the feed forward path and this portion of the equation represents the feedback path. And in the case of a recursive filter, there will be at least one feedback path in the filter. So at least one term will be present in this equation for a recursive filter, whereas in the case of a non-recursive filter, this term will go 0. Let's look at these details in the next slides. Now this is the same equation where xn is the input signal, yn is the output signal. Coefficients going from A0, A1, A2 up to AM and B1, B2, B3 up to BL are actually constants, and these are also known as the filter coefficients. Actually, these coefficients determine the characteristics of the system, meaning by whether the filter is a low pass filter, band pass filter, high pass filter, or a band stop filter. Now, when bk is 0, as I was telling, when bk is 0, the filter is said to be non-recursive type. There will not be any feedback path. When bk is not equal to 0, the filter is recursive type, and this term will be present in that case. Now let's look at non-recursive digital filters, which are also known as FIR filters or finite impulse response filters. Now if bk is equal to 0 in the general equation of the filters, then the calculation of yn does require the use of previously calculated samples of the does not require the use of previously calculated samples of the output. So we need not to calculate for this feedback term. Only the feed forward terms are there. Only the feed forward paths exist. Now, if you expand this sigma, you will get A0, xn plus and so on up to the mth term. Now, this is also recognized as what we call as the convolution sum. Because these AKs, we call these as the filter coefficients. HK in the case of a convolution formula. In the case of when this equation is used to represent a filter, these are known as the filter coefficients. So basically, these are the filter coefficients. Therefore, the impulse response is identical to the coefficients. That is because if you look at the general formula of the convolution sum, so and if you compare this equation with this equation, you will see that HKs are basically AKs only. HNs are basically ANs or AKs only. Therefore, the impulse response is identical to the coefficients. All right. Any filter, and we also know that since capital M is finite, so that means the impulse response will be finite in this case. Any filter that has an impulse response of finite duration is called finite impulse response filter. So A0 basically corresponds to H0, A1 basically corresponds to H1, and so on. Now let's take one example where capital M is equal to 2, right? So yn is given by A0 xn, A1 xn minus 1. This is the present input. This is the input delayed by 1 unit time. This is the input delayed by 2 units of time. A0, A1 and A2 are the filter coefficients, or the coefficients of the system. Now we also know that what is the if you take the Z transform of this equation, right? And you because yn Z transform will be yz, this xn will be xz, and from this equation if you calculate yz by xz, which we also define as the transfer function of the filter, which is hz, and this equation will be given by a0 plus a1 z minus 1 a2 z minus 2. So this is a second order filter because the maximum power of the z variable is 2 here, because if you divide it by z square, if you multiply it with z square, you will get uh, power 2. So this is a second order, this is a non-recursive second order FIR filter. A property of the FIR filter is that it will always be stable, because there is no denominator in the equation. We will look at this point in the next slide. Stability requires that there should be no poles outside the unit circle. And in the case of FIR filters, this condition is automatically satisfied since there are no poles at all outside the origin. In fact, all poles are located at the origin. When we say that there are no poles, the poles do exist, but they exist at the origin. Any zeros or poles located at the origin do not contribute to the transfer function. So this is a stable system because there are no poles, in fact, and there is no question of lying of the poles outside the unit circle in the Z plane. Another property of non-recursive filter is that we make filters with exactly linear phase characters. This is very important. Two things are very important for FIR filters. One is stability, the other is the linear phase characteristics. The ability to have an exactly linear phase response is one of the most important properties of a uh, linear time system. When a signal passes through a filter, it is modified in amplitude or phase. The nature and extent of the modification of the signal is dependent on the amplitude and phase characteristics of the filter. So once a filter passes through the system or the filter, the amplitude and phase will be modified. So uh, now let's look at what is phase delay. When we say that it is having linear phase, what is the actual meaning of the system having the linear phase? We define two terms actually. One is phase delay, the other is the group delay. Now the phase delay or group delay of the filter provides a measure of how the filter modified actually the phase characteristics of the signal. If we consider a signal that consists of several frequency components, the phase delay of the filter is the amount of time delay each frequency component of the signal suffers in going through the filter. Meaning by when we allow to pass a speech signal, for example, through the filter, speech signal will have number of frequency components. So when all the frequencies pass through the system, their phase varies linearly as the frequency increases. That is the definition of the phase delay. So phase delay is defined by this phi is the phase, omega, small omega is the digital frequency divided by the digital frequency. So this is phase delay, negative of the phase angle divided by the frequency, basically. And what is group delay? Group delay is actually the derivative of the phase delay with respect to omega, small omega. And when we say that the phase delay is linear, that means the group delay will be constant. So what is actually the meaning of the group delay? Phase delay means the phase of the signals represent signals for different frequencies vary linearly. In the group delay, it gives an idea of the composite signal. Composite signal means combined all the frequencies. So that will be a composite signal. Now all the frequencies will suffer the same delay while passing through the filter, because if you look at the mathematical formula, it is the derivative. So the derivative of the linear function is a constant function. So that means the group delay will be constant. That means every frequency will suffer the same delay while passing through the filter, while passing specifically through the FIR filter. FIR filters are highly stable and they have linear phase response. The group delay, on the other hand, is the average time delay the composite signal suffers at each frequency as it passes from the input to the output of the filter. So this is the group delay, the negative of the derivative of the phase with respect to the frequency. This is the diagram of the on the y-axis is the phase, and on the x-axis is the digital frequency. So digital frequency can vary from minus pi to pi, because beyond these limits the spectrum will repeat, digital spectrum will repeat. We have already discussed these things. So the phase response is linear with respect to the frequency, digital frequency. Phase response of a linear phase filter. A constant group delay means that the signal components at different frequencies receive the same delay in the filter. We have already discussed it. A linear phase filter gives same delay to all frequency components of the signal. A filter with a non-linear phase characteristics, if for example a filter is there which is having non-linear phase characteristics, will cause a phase distortion in the signal that passes through it, because different frequencies will get different delays. One frequency appears at the output of the FIR filter or a non-linear filter with a different delay, the other appears with a different delay. FIR filters are all linear filters, linear phase filters. So FIR filters will have linear phase response, but if a system does not have a linear response and the response is non-linear, then the frequency components will be delayed by an amount which is not proportional to the frequency, thereby altering the harmonic relationship. Such a distortion is undesirable in many applications, for example, music signal or a video signal. Speech signal will is because our in speech signal this is not a major problem of there is no problem of phase distortion in speech signal, because our ears are not perceptive to phase distortion. But in the case of music and video signals, uh, high quality output is required. So therefore, the filters are required to be linear in that case. Now, the question is that how to test a system, whether the system has linear phase response or not. A filter is said to have a linear phase response if its phase response satisfies one of the following relationships. Now phi of digital frequency is equal to minus a small omega, or phi of omega is equal to b minus a small omega. These two relationships are there, and if we can prove that the phase response of a system has a correspondence with this type of relationship, which are linear relationship. This is a linear relationship, and this is also a linear relationship, but with an intercept present. So if we can prove that the phase response satisfies one of the two equations, then we can say that the system has linear phase response. To prove this and to verify what is said in the last slide, I have an example here where two filter structures are shown below, and we have to show that both the filters have linear response. So this is one filter, this is FIR filter. As there is no feedback path, only feed forward paths are there. This is a feed forward system. This is another feed forward system, no feedback path, and we have to prove that these two systems are linear phase systems. Now let's write the difference equation of the first system, because yn, one path is coming direct, so it is xn. The second path is with a delay of 1, so it is xn minus 1 plus xn minus 2. You take the z transform and you replace z equal to e to the power j omega to get the frequency response of the system. And we normally write, we are replacing z with e to the power j omega, but we will write it as h omega only just for simplicity. And this is equal to, here z will be replaced with e to the power j omega, and similarly here also. Now if you solve this expression, you will get, you will reach up to this point, 1 plus e to the power minus j omega plus e to the power minus j2 omega, once you replace that with e to the power j omega. From this expression, if you take e to the power minus j omega outside the bracket, so the relationship will be reduced to this one. Now we know, by applying the Euler's relationship, we know that cos theta is a e j omega plus e to the power minus j omega divided by 2. So this has to be 2 cos theta. This internal expression can be 1 plus 2 cos theta, and this outside term will remain. Now 1 plus 2 cos omega, it's not theta, it's omega. 1 plus 2 cos omega is actually the magnitude term, and this is the phase term. Now we can say from here that the phase term, which is phi of omega, small omega, which is digital frequency, is equal to minus omega. We can take the term from here, and we know that if we can prove, we know that if phi omega is minus a omega, and that's what we have proved it here, phi omega is minus omega, which is a linear relationship. So this is a linear phase system. Now let's look at the second system. Yn is equal to xn. Once you write the difference equation, yn is equal to xn, and two delays are there in the second path, so xn minus 2. You take the z transform here, hz is equal to 1 minus z minus 2. Replace z by e to the power j omega. Here we are not writing h of e to the power j omega for simplicity. As I have already explained, we will write only h of omega is equal to 1 minus e to the power minus j2 omega. You take out from this expression e to the power minus j omega, and inside the bracket will be e to the power j omega minus e to the power minus j omega. Now we know that sine theta is equal to e to the power j omega minus e to the power minus j omega divided by 2j. So therefore we multiply the expression with 2j and divide the expression by 2j, and this will be equal to sine of omega. And this is 2, and this is twice of j pi by 2 minus omega, right? Because you will get one term outside, which is j, right? So this will be 2 twice of e to the power j pi by 2 minus omega. Now e to the power, now you take the phase expression from here. This is the magnitude response, and phase response will be phi of omega pi by 2 minus omega. All right. So this j factor will actually be pi by e to the power j pi by 2. All right. So j factor is a pi by 2 rotator. Basically, it's a complex iota term, j term we call it. So once you replace j with e to the power j pi by 2, so uh, you can uh, you can combine these two terms and you can get this term. So we know that now the phase term is phi of omega is pi by 2 minus omega. So this which resembles with the second equation. So therefore we can say that this is also a linear phase system. That's how we can prove that a system given is a linear phase or is having a linear phase response. Now let's come to, so previously we have discussed about the FIR filters, and let's now concentrate on recursive digital filters, which are basically infinite impulse response filters. And every recursive digital filter must contain at least one closed loop. That means there will be one feedback, at least one feedback path. So that means BKs are not zero here. That's what is said for recursive digital filter. BK is not equal to zero. So this term will be present. In the case of FIR filters, only this term was present. There was no term with these BKs. And each closed loop contains at least one delay element. So there has to be one delay element because this represents the previous output samples. So there has to be one delay element at least. Now let's take one example with a0 equal to a0 and uh, so with rest of the AKs are all 0 for k greater than 0. So that means the equation, as I have defined the specifications here, the equation will be reduced. The general equation will be reduced to yn is equal to a0 xn minus b1 y of n minus 1, because all the rest of the bk's are 0 for k greater than 1. Now if you take the z transform of this difference equation, you will get yz by xz, which is our hz, is equal to a naught divided by 1 plus b1 z minus 1. This is an IIR filter because you have the denominator term, right? So any denominator term, that means having poles. So this is an IIR filter. FIR filters will not have any poles because there is no denominator term. Whereas the IIR filters can have zeros also and poles also. So that's what is said here. A recursive filter is an infinite impulse response filter. Now let's take examples. Hz is equal to a naught. So this is a feed forward system. This is a second order FIR filter because this Z is the highest power of Z is minus 2. So therefore it's a second order FIR filter, only zeros. This system has only zeros, no poles are there. Therefore this is an FIR filter. Now let's take the second example. This is again a second order filter because the highest power of Z is 2 minus 2. But this is an IIR filter because it has got poles, and this system has got only poles, no zeros are there. So therefore this is a second order IIR filter. Let's take the third example. In the third example, you have the numerator term also and the denominator term also. So that means this is an IIR filter because the denominator term actually represents the poles present in the system. So therefore this system has got poles also and zeros also. So once a system has poles, this is an IIR filter. All right. Now this is also very important because poles and zeros both can be real or imaginary. Now let's take one example where hz, the z transform, the impulse response z transform is given by transfer function. This is the transfer function of the system in z domain is 1 minus a to the power a into z to the power minus 1, where a varies from 0 to 1 only, open interval. If you write the difference equation from here, how you will write the difference equation? Yz by xz is basically our hz. You take 1 minus az to you cross multiply and take the inverse z transform, you will get the difference equation. So our difference equation for this expression is yn is equal to xn plus a of yn minus 1. It has got one feedback path, therefore it is an therefore it is an IIR filter. Now we must also calculate the DC gain of the system. Now what is DC gain of the system? The DC gain of Hz can be obtained by substituting small omega equal to 0. That means zero frequency. So at zero frequency we can calculate the gain, which we call as the DC gain of the system. Now in this expression we replace z with e to the power. Once we have to get the frequency response of the system, we can get that by replacing z equal to e to the power j small omega. So but we will write here only omega for simplicity purpose. So that in this expression now we need to calculate the DC gain. So h omega at small omega equal to 0, so that means zero frequency. That means we are trying to calculate the zero gain, DC gain. In this expression you put the value of omega to be 0, so this comes out to be 1 over 1 minus a. So 1 over 1 minus a DC gain is present in the system. Now if DC gain is undesirable, if you don't want the DC gain to be present in the system, we can introduce a reverse reciprocal constant. So the DC gain is 1 over 1 minus a. In the transfer function we can introduce 1 minus a term, so that the DC gain is cancelled out. So by effect introduce a constant gain factor of 1 minus a, so that hz becomes this, and there will be little modification also in the difference equation, so that the DC gain is cancelled out. DC gain is 1 in this case. All right. In the earlier case, the DC gain was 1 over 1 minus a, but once we have compensated for the DC gain, the DC gain becomes 1. Let's take another example and try to solve this question. Now consider a low pass filter. So this difference equation given is of a low pass filter. We have to determine the value of B, so that modulus of h0, meaning by the DC gain, is 1, because modulus of h0 means our omega is 0 here. So once the DC gain is given to be 1, so we have to determine the value of B, and we need to determine the 3 dB bandwidth for the normalized filter in part 1. So for the first time I'm introducing here the 3 dB bandwidth of a filter. We will see what is the how to calculate the 3 dB bandwidth for the, and normalized means where the DC gain is 1. We have normalized it to 1. Now let's try to solve this equation. This difference equation is given, so once we take the z transform, we can get the transfer function equal to b over 1 minus a z to the power minus 1. Now we calculate the frequency response, right, just by replacing z with e to the power, this has to be omega here, by z to be e to the power j omega. And we are also given that the DC gain, which is for omega equal to 0, is given to be 1. So that means this expression, once we put omega equal to 0, we say that the DC gain, which is h0, is equal to b over 1 minus a, and given this value is 1, so we can calculate the value of b in terms of a. The b comes out to be 1 minus a. So we can modify the transfer function by this calculated value of b, and our transfer function or the frequency response becomes 1 minus a divided by 1 minus a to the power a into e to the power minus j omega. We can expand, we can further, now there are two things are there. Once the frequency response is given, from the transfer function we can get the frequency response by substituting the value of z with e to the power j omega. So once we get the magnitude, once we get the transfer function, we can calculate the magnitude response from there, which is the modulus of h omega, and we also need to calculate the phase response, which is the angle of this complex term. Now we can expand this term e to the power minus j omega equal to cos of omega plus j sine omega. So this expression will become will take this form. And how to calculate the magnitude response? Just take the square and take the square root of the complex of the real and the imaginary terms. So this is our real term 1 minus a cos omega plus j a sine omega. This is our imaginary term, and we take these squares and take the under root. So 1 minus a remains because taking the square and square root will give me 1 minus a only. So my magnitude response becomes this expression. Now if you expand this 1 minus a cos omega whole square, this term will be cos square omega, and you can reduce this expression by cos square omega plus sine square omega is equal to 1. By applying that formula, this expression will reduce to this one, 1 minus a under root of 1 plus a square minus 2a cos omega. There is one second method of also to calculate the magnitude response. So h omega is given to us. So this is basically h omega. H omega is given to us, and multiply it with the complex conjugate of the of h omega. So if you multiply this one, our h omega is 1 minus a e to the power minus j omega, and take the conjugate, this j term will become plus. If you multiply the two terms, you will get the magnitude square, and then take the under root, you will get this term, which is equal to the previous formula. Right. Now we need to calculate the 3 dB bandwidth also. Our DC gain of the system. So this is the frequency response, right? We have to calculate the 3 dB bandwidth. Now 3 dB bandwidth is basically this DC gain is 1. The 3 dB bandwidth is actually 1 over under root 2 of the gain. That means 0.707 of the gain. And in terms of power, this will be this point is known as the half power point. That means the power will be half. So this is DC gain, square it, this will be half. So this will be our h omega square, magnitude response square, for this omega equal to omega c, because this point is 1 over under root 2 of the gain. That means 0.707 of the gain, and corresponding to this, the frequency is known as the cutoff frequency. This is basically a low pass filter. So if we calculate the 3 dB bandwidth, the corresponding frequency will be omega equal to omega c, and this frequency will be known as the cutoff frequency. And for this frequency, so this is the half power point. From here we can also calculate the cutoff frequency of 3 dB bandwidth, or the cutoff frequency of the low pass filter, because in this expression we know the value of DC gain, and we know this expression. Now this half is for the DC gain, and this is the expression for the magnitude response, magnitude square response. And from here we can calculate the omega c, which is the cutoff frequency, and is given by cos inverse of minus a square plus 4a minus 1 in the numerator and 2a in the denominator. So this omega c is basically this frequency, which is the cutoff frequency for this low pass filter, and it defines the bandwidth of the low pass